So welcome everybody, and welcome James to today's seminar. Today we're going to be having a presentation on the importance of mechanical material properties and a critical appraisal of mechanical testing methods from James Dean, our presenter today. But first, I'd like to tell you a little bit about EIS and what we do and our background. So the EIS is a long-established charitable organisation, and we focus on areas in fatigue analysis, testing, durability, sound and vibration. There's a whole wealth of members in the EIS, and there is a massive number of years of experience with us all, gained through working in some of the best-known companies in the industry. And what we do as a collective is to organise seminars, webinars, exhibitions, conferences, workshops, to share this valuable information with the rest of the society and with you guys that can join us today. One of our main charitable events that we run is the Young Engineers Forum, which is where this seminar has come from. And the aim of that forum is to focus on engineers at the start of their careers through webinars like this, seminars and events. Some of those events are like the exhibition that we hold every year, which is an opportunity for everyone to get together, look at some new and interesting technologies, and also to join in with some mini seminars. So about our presenter today, so we've got James Dean, who has a wealth of experience and degrees and all sorts, most notably from Cranfield and Cambridge, and has moved through various research positions and have seems like you've got quite the background in starting businesses, and you're now the CEO of Plastometrics.
That's
so
right.
If you would like to take over now and give yourself a little bit more of a introduction and go through today's content, I'll leave you to it, and we'll come back at the end for some questions which everyone can answer or ask in the chat as we go through. I will monitor them and then we'll go through them at the end, if that's okay.
Yeah, thanks, Jamie. Appreciate that. So thanks again for the introduction. Really nice to be here today, and really nice to have this opportunity to present a few slides on, well, mechanical properties and also mechanical testing methods. And like you mentioned in the biographical intro, I'm a material scientist by training and background, and I actually started my love affair with materials, if you want to call it that, and mechanics almost 20 years ago, and I continue to believe quite strongly in the importance of mechanical material properties, especially with respect to the industrial world that we live in. So in today's presentation, what I'm hoping to do is take us on a short journey around this important field by covering some of the more fundamental aspects of mechanical properties and also of materials testing. Although given that we've only got this webinar, I'll aim to keep it fairly focused where possible, although this naturally means that we can't cover everything that we might otherwise want it to. It's perhaps also worth noting that this journey that we go on won't necessarily be a linear one. I'll be moving around a little bit, although I'll try to keep the story coherent, and I've certainly also tried to keep the coverage and content lightweight and simple to follow. So apologies to those in the audience who might already have a strong background in this particular area. Okay, let's start though by asking ourselves a very simple question, which is why is mechanical testing important? And there's actually lots of reasons why, but my stock answer is that everything is made from something, and that's kind of obvious, yet we're also familiar with our everyday world that we rarely stop to acknowledge this fact, this rather important fact actually, that it's essential that the materials that we use and the products that we use are fit for purpose, safe to use, compliant where necessary with the regulations, are appropriate for their intended tasks, because if they're not, then Well, it can be maybe mildly annoying, like when you crack the screen on your iPhone maybe. Or at the very extreme other end, it can be fatal, like, for example, when an airplane engine component suffers from a mid-air failure. So having some type of understanding of mechanical properties and maybe more importantly, having the means and the methods to measure them is actually really rather important. So I've listed a couple of examples as to why material property measurement is important on the slide here. So evaluating product designs, these are all fairly obvious. Selecting appropriate materials for certain applications, maybe verifying a production process, like an annealing treatment maybe. Or in some cases, things like asset integrity monitoring is quite important too. So monitoring things like degradation of properties over time, maybe at a oil and gas rig or a nuclear power plant or something like that. So there's just a couple of reasons why measuring mechanical properties is important, but there are many others. Now, the degree of that importance is actually reflected in this slide by reference to the current market size for testing, inspection and certification services. And that is a market actually that continues to grow. So, and some of this might be of interest for any people in the audience that themselves are interested in the commercial market drivers, because they rightly include things like safety regulations, and that's very important. But the market right now is also being driven increasingly by things like environmental regulations, especially as we try to pivot to a greener economy. And we've got all of these new or enabling technologies that are coming onto the market right now, electric vehicles being just one example. Anyway, that's probably the first small deviation from the core presentation topics, although like I said, the journey won't be linear, so we'll try to get back on track. I just wanted to give that kind of context as to what's driving a lot of our interest, not just from a technical point of view, but also from a commercial point of view in mechanical materials testing as well. Okay, what about then just a very quick, very brief history of mechanical testing methods? Well, we've been interested in mechanical properties since the Stone Age and through the Bronze Age, and from the Bronze Age to the Iron Age and to the, well, if you want to call it the Silicon Age now, or whatever. But the importance of materials has been recognised throughout history. And in fact, one of the most important attributes of materials is their strength characteristics. And through time, as we can see on this slide, there have been many different tools for measuring the strength of materials. And the oldest of those actually is the common hardness test, which dates all the way back to 1722, when actually hardness tests took the form of scratch tests, actually. Sometime later, around 1890, early tensile test machines started to become available. And in fact, the tensile test since that time has remained the gold standard in mechanical testing, and it continues to be the go-to method for measuring things like stress strain curves. But it does suffer from some limitations, and we'll maybe cover some of those in a few slides' time. Also emerging at about the same time, early 1900s, was the Charpy impact test, which can be used for measuring things like the fracture energy or the toughness of materials. And that technique is popular because it's very simple and it's very easy to prepare the specimens, and it therefore continues to be used extensively, much like the common tensile test. But we would say that, like time itself, technology continues to move on and new capabilities emerge, and indentation plastometry, which we'll cover today, is a new method for measuring stress strain curves and metal strength parameters. But we feel, and we hopefully we can show later, that it's well, simpler and quicker and more versatile than conventional mechanical testing. So more on that later. Okay, well, the most common mechanical properties that are measured, routinely at least, are the ones that are listed here. And these are things like stiffness and strength. Sometimes that term is quite well, or quite poorly defined actually. Ductility, toughness and hardness. But a common question we would ask is, what exactly are these properties? What do they mean? How do we define them? Because my own experience, both when I was at the university in Cambridge and also with through my interactions with industries, that these terms are sometimes confused. And even when they're not confused, there can be some subtleties and some nuances that tend to get lost. And these can actually be really quite important when it comes to interpreting materials testing data, which is why my presentation today is really geared towards trying to clarify some of these points. The first two properties that I want to cover, albeit fairly briefly, are stiffness and strength. And while defining these two properties, it's actually helpful to do so by looking at a stress strain curve. Okay, so that's what I intend to do. And if we take this one, and the one that I'm showing here is just an arbitrary example of a stress strain curve. And on the left hand side is a common stress strain machine, if you like. But just note one thing, which is that the behaviour that is being shown in that particular graph is specific to metallic materials, which is where today's discussion is focused. Other materials behave slightly differently. And I'm assuming that most people, if not everyone in the audience here today, is reasonably familiar with the tensile test and the universal mechanical test machine, in which a test coupon, which is shown in blue in that image, is stretched or strained, if we want to use the correct term. And while being stretched, the forces that are needed to stretch it are being continuously monitored. Now, a key feature of this test is, which is perhaps a little bit more subtle, is that the stresses and the strains that are developing within the central section of that specimen are, well, one, uniform, i.e. take the same value, and two, uniaxial, i.e. oriented in one direction along the testing axis. And when you do such a test, a number of features become apparent. And the first place I want you to focus your attention is section A on the graph, which is the region represented by a straight line. Because in this region, the material is being stretched, or strained rather, but in a way in which the stresses and the strains are related to each other in a linear fashion. And that relationship, that linear relationship, it continues to hold until the stresses reach point B on this graph. Okay, and then beneath the stress at point B, the material is still deforming elastically, which simply means that the material will recover its initial shape if the load that's been applied is removed. And again, this is all very simple, probably familiar to everyone. Nevertheless, the gradient of that linear part of the graph represents the stiffness of the material, or its elastic modulus, which can therefore be defined in this context as a material's elastic resistance to applied forces. And I think probably all of our experience and intuition tells us that, for example, metals are stiffer than plastics, so we already actually have some sense of what the stiffness of the material really means. And again, apologies possibly due here to all those in the room that already understand all of this, but it's just helpful to cover some of this at least as a gateway into slightly more complex behaviour in the next few slides. That more complex behaviour is in fact plastic deformation, and in fact understanding plastic deformation, again with reference to this particular stress strain curve, should allow us to draw some definitions for strength. So the highlighted location is now point B, and this is the stress at which the material begins to deviate from its elastic behaviour that we previously defined to plastic behaviour, such that the material beyond this point will no longer return to its original shape once the load has been removed. And again, we all have an intuitive sense of what this means, because I'm sure at some time or another we've all bent a metal spoon or another piece of metal into some new shape, and maybe what we didn't understand at that time was that the material we were distorting did at some locations contain stresses that were in excess of the stress at point B, so it went on to yield. Okay. Now, the second relevant location on the stress strain graph from a strength definition point of view is the ultimate tensile strength, which again I've highlighted here, which is basically in its simplest form the maximum nominal stress that was reached during the tensile test. Although it's actually worth noting that it's not always very well defined when you see real stress strain curves, and sometimes what you'll observe is something looking more like a plateau in that region. Okay, so it's not always as well defined as it is in this particular graph. Anyway, before we settle on the definitions for strength, it's maybe important to highlight what's actually going on between points B and C during a tensile test, because during this particular stage, the tensile test specimen is straining, or stretching if you like, but it's doing so uniformly, which really just means that as the specimen gets longer, the cross-sectional area is getting smaller too, but it's doing so uniformly, i.e. the cross-sectional area is the same at every instance, all the way down the length of the central section of the testing coupon. Okay, so that is uniform plastic straining or uniform elongation of the specimen. Once we reach the UTS though, or the ultimate tensile strength, things begin to change and the test specimen actually starts to neck. And you can see an example in the inserted image where at this point the stresses and strains within the specimen actually no longer remain uniform or uniaxial, as is the case during the uniform straining portion of that test. They become far more complex than this, and at that point interpretation of these curves becomes much more difficult as the material is now heading very fast towards its final failure stage. So taking that from a very simple analysis of the stress strain curve, we can begin to draw a definition for the strength of material, and in fact it's possible to define two in this context, one being a material's ability to withstand loads without plastically deforming, and that would be the yield strength, okay, point B, and one being a material's ability to withstand loads that mean it doesn't start to fail, which is the ultimate tensile strength. And as we said, beyond there, the material is then heading very fast towards its ultimate failure. Okay, so there's two definitions of strength emerging from that stress strain curve. Then I think they're very important to distinguish and to clarify. What about then ductility? Those of you looking closely at that stress strain curve would have noticed a fracture point at the end and therefore a fracture strain. And it's important we talk about ductility because it's a property that gets cited very heavily, and of course it's related to fracture of the material and therefore failure. So quite naturally it assumes a fairly high importance, especially when we try to think about designing structures and/or materials for safe operation. So actually, let's start this time by first defining what ductility is. And it's really a material's ability to sustain plastic deformation before failure. So it's about the degree of tolerable strain. Okay, and that definition actually is, well, I would say completely uncontentious. I think everyone would agree that's what it is, and that's apparent on the stress strain curve that we're showing here. But there's something rather important about ductility which is not always very apparent, and it's something that is less well understood, which is that ductility, or ductility values, which are nominal strain values at fracture, well, a ductility value is not a fundamental material property, like, for example, the yield stress is. Okay, it's really important, actually. The ductility that is measured in a normal tensile test actually varies, it changes, if you change the dimension of the test coupon that you use. And I know from my conversations with people in and around the various industries we work with, and also in the universities that we work with, that this is not always appreciated. But it's extremely important to understand and recognize this. And I'll explain why. So here are some real experimental tensile test data, all being conducted on the same material. Okay, and this data shows that the ductility value falls as the specimen aspect ratio increases. Now, the curves are actually almost coincident up to the ultimate tensile strength, and that's exactly what should happen. That's exactly how it should be. But once that necking process starts within the specimen, then the aspect ratio starts to have a very significant effect on the measured test outcome, specifically on the ductility value. So when people therefore cite to you a ductility value, it's often, and I don't mean to be contentious, but it's often totally meaningless. If you search the literature looking for ductility values of a particular alloy, and there's no information about the test specimen dimension, then that information is also meaningless. The only real way that a ductility value can be used is to rank different materials that have been tested using the exact same specimen dimensions. Otherwise, ductility values are actually a very limited engineering utility. Okay? And as one example, and we won't name names, we've worked in the past to help a company that were using ductility values, measured nominal strain at failure in their finite element calculations or crash simulations, not understanding that it's totally sensitive to the specimen dimensions they were using in their tensile tests, and it's made a big difference to the predicted outcomes from those FE simulations. So it's something that's not well understood, but it's something that's crucially important in some cases because, of course, it's related to fracture and failure. Okay, what about Toughness then, also important because it too is related to fracture and failure. It is the fourth property on our list of mechanical properties as we seek to work our way through these. So with this slide, what I'd really like to do as well, much like with ductility, is quash a fairly common misunderstanding, which is that the area under the curve, the area beneath the stress strain curve, is equal to the toughness of the material. This isn't right, although it's easy to understand where the confusion arises. And one way of very simply confirming that this is not quite right is to simply compare the units of toughness, which can be expressed in two slightly different ways, either joules per meter squared or megapascal root meter, and compare those with the units of the area under the curve, which is just joules per meter cubed. So the two are dimensionally inconsistent, okay, which is one indication that they're not the same thing. The definition of toughness is actually a material's resistance to crack propagation, whereas what we have in the stress strain curve above in this slide is a load of uniform plastic deformation, a load of uniform plastic straining that's taking place between the yield stress and the UTS. And this is not plastic work that can be associated with crack propagation. Okay, that's really important. It's not plastic work that can be associated with crack propagation. So this area underneath that curve, this total area, cannot be considered to be a true measure of the material's toughness. Unlike ductility, though, it's not totally meaningless. If we can see that the area underneath that curve is large, then that does imply that a material will be tougher. Okay, so there is a correlation in this instance between this area and the real toughness of the material, but it fundamentally isn't the toughness that is being measured here, and it's really worth clearing that up again because, as with ductility, it's related to failure and fracture of the material. So it's really important that we understand these differences and these nuances. In fact, if you want to measure the toughness of material, the true toughness of material, or its fracture energy, or something like that, then it's best to use something like the Charpy impact test. And we indicated early on in our historical overview of mechanical testing that this arrived on the scene in around the early 1900s. And this is a much better way of measuring toughness of materials because it directly measures the energy absorbed during a fracture test, okay? And it's the energy absorbed purely related to the propagation of a crack. So note, for example, in the specimen, in the top of this image on the left-hand side, that the specimen has been deliberately notched, and that's in order to drive the crack in a particular direction and to make sure that the energy that's been absorbed is being absorbed only through the process of that crack propagation event. Okay. All right, so we've done stiffness, strength, ductility, and toughness, and we're now going to move on to hardness. You know, some of the reasons why these terms get confused is they're often related to each other, actually. Strength, for instance, and hardness are quite closely related, although not in a way which is easy to define. So let's again start by defining what hardness is, and it is specifically a material's resistance to plastic deformation. And since we're all now really familiar with the stress strain curve, we can understand this definition in view of what we know about the yield stress and the hardening behavior of material, and I've tried to highlight that in this plot. Okay, so if hardness is basically a material's resistance to plastic deformation, then quite naturally and quite obviously materials with high hardness tend to have high yield stress values and or high work hardening rates. The work hardening rate being the rate at which the stress approaches the ultimate tensile strength from the yield strength. Okay, so the hardness number is therefore very closely related to the stress strain curve, ergo the strength of the material. But importantly, what you cannot do is infer or calculate what the stress strain curve looks like simply from a hardness number. Okay, that kind of translation is impossible to do, actually, and maybe more on that later. The reason though why we like hardness testing, apologies, I changed the slide there while I was talking. The reason though why we like hardness testing, and most people are familiar with hardness testing, is because it's extremely simple to do. It's very low cost, Sample preparation is minimal. You can test very small volumes of material. You can map properties across a surface. You can do testing at high and low temperature if you want to. You can test real components, and if you want to, you can even do things like test components. Okay, that's some of the reasons why we like hardness testing. And the process is very simple insofar as you simply take a very hard sphere or a pyramidal type shape or a conical type shape, and you push it into a material that's a little bit softer. And you can measure things like I don't know, the diameter of the spherical indent or the diagonal across a pyramidal indent or something like that. You can measure a hardness number, and that's all very simple and very easy and reasonably intuitive as well. Next slide. And that's partly what explains the reason as to why hardness testing is used so extensively. It also explains why hardness tests have been around for hundreds of years. The problem though with hardness numbers, this is the crux of where I'm trying to get to, is that a bit like ductility values, hardness numbers are not fundamental material properties. The hardness number of a material actually changes if you change the shape of the indenter that you use or if you change the load that you apply. So hardness numbers can only really be used in a very semi-quantitative way to rank materials. Okay, and I've said in the slide there as well that they can't really be used in proper engineering calculations. And what I mean by that is that they can't be used, for example, in a finite element calculation or a structural safety calculation. They're also often ambiguous, and they can be misleading if they're being used as proxies for strength. So, for instance, in the graph on the left-hand side, there are two materials that I've shown, two stress-strain curves. And quite clearly they have substantially different stress-strain behavior. Okay, one has a moderate yield strength and the other has a fairly high one, and one has little work hardening while the other work hardens much more significantly. Yet despite this, these two materials, they both have similar hardness numbers at about 250 kilogram force per millimeter squared in this case. And therefore you couldn't actually distinguish these two materials on the basis of their hardness numbers alone. And you'd be ill-advised, in fact, to design something thinking that the yield stress might be close to 800 megapascals off the back of a hardness test when it could in fact be closer to 400 megapascals. And the reason that I raise that is because some people try and equate a hardness number to a yield stress by invoking a factor of 3 between those values. Okay, so it's actually very dangerous to do that and can lead to all sorts of problems. Okay, so while the test is simple, quick and easy, the problem is that the data that you get is to some degree also meaningless. That's maybe slightly too strong. Okay, so mechanical testing or uniaxial mechanical testing, as we talked about before, is unquestionably the gold standard. We mentioned that in a previous slide for characterizing the strength of materials, but it too suffers from some limitations. They can be addressed in most cases, but these might include the fact that the machine is very expensive, so you have high capital setup costs. Time consuming as well. Really what I mean by that is not the test itself, which tends to be quite quick. It's actually the preparation of specimens, because you've got to get coupons machined and you've got access to machining facilities, or you've got to outsource that process, and that can take quite a lot of time. But in addition to that, you need to make sure that the material can be machined. Not all metals are very easy to machine. You can suffer from clamping and slippage difficulties or compliance in the system. You can't, of course, test real components. You've got to machine coupons, and also what's not possible, like in hardness testing, is mapping of local variations in properties. Okay, so some limitations there. Okay, so there is a technique though, which in our point of view, accepting of course that we're biased, combines the very best attributes of the tensile test, which is acquisition of full stress strain curves, with the very best attributes of the hardness test, which is ease and simplicity of testing, and this is indentation plastometry. In fact, to give it its full title, it's actually called profilometry-based inverse finite element analysis, indentation plastometry, but that's too long. So by way of proper introduction, what I've got here is a video. It's a rather sort of fancy animation. There's no sound, so please don't expect any sound on this one. Here you'll get to see one of these indentation plastometers. You can see that it looks similar in execution to hardness testing, actually, so that machine there is performing an indent. Only this time we're coming along with the integrated profilometer, and we're measuring the full profile shape because that profile shape contains an awful lot of information, and then it goes into our software package, SnapShape, where we do some clever optimization work and some inverse FE, and we're able to pull out meaningful data like full stress strain curves, strength parameters. We can even calculate hardness numbers if people so want them. And this entire process takes just a matter of minutes. It's extremely quick, 3 minutes, in fact, sub 3 minutes. So that was the plastometer video. But let's move away from the flashy commercial animation, because that's where I don't want to spend my time, and come to the substance of the method and talk a bit more about the science, because the method involves just a few very simple steps that are fully automated. The first is that, as we saw in the video, we indent the sample. The difference at step 2 between that and hardness testing is that we measure the full profile shape. And we do that because we know, as I mentioned, that the full profile shape contains an awful lot of information about the way in which the material is deformed, and therefore an awful lot of information that can be used to back out or infer the underlying stress strain behaviour. And to do this in our software package, we analyse and operate purely on the residual profile shape, nothing to do with the load displacement curve. And we have this algorithm which returns the stress strain curve very quickly. If you are interested, not everyone is, but I'll present it nonetheless, in what that algorithm looks like, well, it's conceptually very, very simple. The process involves conducting the experiment and measuring the residual profile shape. Okay, but what we then do is run an equivalent indentation finite element simulation, and in that model we have to specify some constitutive plasticity equation, and we can then iteratively adjust the free and unknown parameters in that equation until the measured and predicted profile shapes converge. And while we do this, we monitor the goodness of fit between measured and predicted data, and I guess our objective, or the objective of our software, is to minimize this difference. Okay. Now, like most optimization problems, there are issues of uniqueness to consider, where uniqueness really refers to those situations in which multiple combinations of the input parameters yield acceptably good agreement between measured and predicted profile shapes. But during the course of our research work, we've looked at this in great detail, and we've been able to implement both experimental testing protocols and some computational protocols that allow us to very rapidly identify the unique combination of parameters that are representative of this material. Okay, so this framework that we've implemented for doing this, it enables us basically to converge on the solution very quickly in just a few seconds. So the approach that we're describing here is best described as an accelerated inverse finite element technique. Now, let's see what that looks like in reality. What these plots show is the iterative evolution of those free parameters in a constitutive plasticity law that begin to converge after about 50 iterations. Okay, and what's also shown in the top left is a parameter called S-red, which is the parameter describing the goodness of fit between measured and predicted profile shapes, and it too converges after about 50 iterations, and that forms the basis for the analysis being stopped. Okay, and on the lower right-hand side, I'm simply showing an equivalent plastic strain field from an indentation finite element simulation, showing that peak plastic strains of around 60% exist within the material when you do these type of tests, and that is a complex three-dimensional strain field, and that complexity is important because that complexity cannot be captured in analytical methods for inferring stress strain curves from indentation test data. Despite people and organizations and institutes trying to do this, this level of complexity can only actually be captured by employing tools like FEA. Okay, it's really important as well. Anyway, let's look at a validation example. Let's get to the core of this. And what we can see with this particular piece of Inconel is a micrograph on the left-hand side showing one of those indents. You can see that it's nice indent. One of the nice features actually is that when you use this technology, you indent a reasonably nice surface, the local microstructure reveals itself, and you can get a sense straight away as to what the grain features look like, what the grain size is, etc. Okay, it's a side thing, but it's very interesting nonetheless. maybe more importantly, on the right-hand side, what you can see is a comparison between the stress strain curve measured using the conventional tensile test machine and the stress strain curve that was inferred using the indentation-based method. And naturally, the agreement is very good. I'm sure you wouldn't expect me to show anything else, but I think important to point out that the key features are being captured here. That is yield stress, hardening behavior, and of course the UTS. And in fact, in more recent versions of our software package, we also pull out post-necking behavior as well. So you can see from that micrograph that our indents are comparatively large, at least when compared to those that are produced by, for example, nano indentation, or even maybe those that are produced by a normal Vickers hardness test. And this is deliberate. Actually, we deliberately indent materials on a fairly large or coarse scale. They're still quite small, don't forget. That indent that's on the screen right now is only about a millimetre in diameter. So it's still comparatively small. It's just bigger than things like nano indentation. Now, the reason that we indent on this scale is because the purpose of our technology is to extract bulk or engineering properties, and that means that you must be indenting a representative volume of material. You absolutely must be capturing all of the microstructural features that give rise to the macroscopic stress strain behavior that you would measure in a common tensile test. You know, if you're indenting into a single grain, as you might be doing in a nano indentation test, you simply cannot get bulk mechanical properties. Okay. And in fact, some of those microstructural features that I'm talking about are actually listed in this slide, and they include things like the crystal structure, the grain size, texture. Grain boundary structure is really important to macroscopic stress strain behavior. You know, full alloy composition, impurities, the presence of precipitates, you know, what is the dislocation density? All of these things contribute to the behavior that you see in a macroscopic tensile test. So you have to interrogate that with your indent. Now, the other advantage actually of indenting on this scale is that issues such as surface roughness, contamination layers, oxide scales, thermal drift, well, these all diminish in importance when you indent on scales like this, which makes the test really reliable and very robust, you know, very repeatable data. And it just makes the whole testing procedure much, much simpler. Okay, I'd now like to show you, just for the last 10 minutes before we go into questions, just a quick case study of indentation plastometry in action. I'll try to keep it brief. It is an example coming from the mining industry, actually. And in the mining industry, they, of course, are naturally interested in trying to break rocks. There's many ways in which you can do this. What the mining industry is trying to do right now is develop new methods for breaking rocks, methods that are greener, more efficient than existing methods. So they're designing new equipment, new comminution equipment, as it's called. And there's an example CAD image there of a particular type of comminution apparatus. And inside that apparatus, you've got these rotating components, which have got these very hard rotating flingers attached to them, and they rotate extremely fast, thousands of RPM, actually in some instances. And what happens in these machines is quite simple. You put the big rocks in at the top, they go in, they get smashed about, and then you get small rocks out of the bottom. Okay. The purpose of these calculations is to help design a system that is more efficient at breaking rocks and to try and control the size distribution of the rocks coming out. Okay, so it's quite a complex process. Also of importance, though, is the wear performance of the system, which is often life limiting. Okay, and to be able to predict or calculate wear performance, you need to know something about the strength of the materials as well, and performance under things like abrasion. So this particular company have been doing some simulation work, and we can see an example in that video there of one of those rocks being broken, and that's all very interesting, quite nice. You can see something slightly more localized in the animation on the right there. And as I mentioned, the material properties of the tools that are being used to break these rocks are really important, okay, for helping to predict wear life. Okay, so understanding what those properties are is really important, because that data can be used to help design the components to maximize life, and therefore efficiency, and therefore return on investment as well. So if we look at those flingers in slightly more detail, there's two examples in this particular image, and they're manufactured from Hardox stainless steel. And on the right hand side, you've got Hardox stainless steel in its as received condition, which is fine, but on the left hand side you've got one of those components which has had a tungsten carbide insert brazed to its front surface, and of course that is designed to help prolong the wear life of the components. Okay, The challenge here, though, is that that brazing process is done at very high temperature, over 900 degrees, and it's over a prolonged period of time as well. And there is a concern, quite rightly, that that brazing process and therefore that heat treatment was deleteriously affecting the mechanical properties of that steel, and therefore possibly affecting the wear life of the steel, which would be life limiting again. So the objective of this particular study was to characterize the strength characteristics of these materials using indentation plastometry, because it simply wasn't possible to do this using conventional tensile test machines. So what we did then, as you can see in that video, is we took these two components. What we had to do with the one that had been brazed, though, was essentially remove that surface oxide layer, which is quite a sensible thing to do, because in that particular case it was very thick. So we've cleaned it up, and it's had a polish and a grind. And then those materials have been inserted into indentation plastometry. You can see an indentation process taking place there. I think the video at this stage is being accelerated in time. Once that indent is done, you'll see the profilometer coming across. That now is measuring the shape of that profile. Also takes a minute or so, but it's been accelerated here. And then once you've measured that shape, you can import that into the software package and you can calculate stress strain curves. Okay, so it's very simple. You can see in the graph, in the image now there, sorry, in the video, this array of indents that's been created on the as received material and on a material that's been subjected to this high temperature brazing process. So let's look at what we were able to achieve then. Well, first off, if you compare the equivalent locations from those specimens, you can see in the right-hand side in that graph that their stress strain behavior is very different. Their strength characteristics are different. And in fact, the brazing treatment or the heat treatment has led to a detectable drop in the yield stress of that material. So it's not as hard as it was. It's also not as strong as it was. Okay, and that type of detailed information simply cannot be picked up in a tensile test. Very, very challenging to capture that. Okay. Now, that is just a comparison between two locations, corresponding locations. But it's possible to do the same analysis across the grid of indents, and the red bars in this bar chart are for the brazed sample, and the green ones are for the annealed sample, for the as received sample. And you can see quite clearly that brazing treatment has substantially affected the yield stress in all of the locations that were tested. Okay, so there's essentially been a uniform reduction across the entire specimen, okay, but just to different degrees. Okay, so that's really useful information, and once you know spatial variations in mechanical properties like this, you can actually predict spatial variations in wear rates as well, and then get a better handle on what the wear performance and the wear life of these components will really be. Okay. Now, to finish this off, I want to show something else, which is that this is the corresponding hardness data. So same materials, same brazing processes, same locations for the indents, but this is hardness numbers, Vickers hardness numbers actually, instead of strength characteristics. And what you see here is that the picture is more ambiguous than it was with the yield stress, less clear about what's happened. And in fact, from the data that you can see here, it would almost look as if there'd been no real consistent change in the strength of the material or the hardness of the material. And it's because the hardness numbers, as I mentioned before, can be really quite ambiguous and quite insensitive to differences in stress strain curves. And we showed an example of two very different stress strain behaviors giving very similar hardness numbers in the previous slide. Okay, so it's just a really important point that's worth thinking about when thinking of whether or not to use hardness numbers. Is there something better you can do? Can you get more information for something like an indentation plastometry test? And of course, our biased view would always be that you can with something like indentation plastometry. Finally, let me summarize what we've done today. We took a brief look at the history of mechanical testing after listing a few reasons why you might conceivably want to do mechanical testing. And we also spent one slide looking at some very simple market drivers, if they weren't already apparent. We then spent a substantial amount of the time looking at the features of the stress strain curve, albeit in a fairly simplistic way, but in order to help us define and understand some of the more common mechanical properties that we're typically interested in measuring, and then we sought to clarify in some instances around ductility and toughness, some misunderstandings. We then took a very brief look at hardness numbers and came to understand that despite the ease and simplicity of the test, hardness numbers themselves are rather limited in their engineering utility, but also, as we've just seen in the previous slide, slightly ambiguous in their meaning. We learned of a new technique called indentation plastometry, which appears to combine the best attributes of both the hardness test, i.e. ease and simplicity of testing, with the very best attributes of the tensile test, which is access to full stress strain curves and proper strength information. And then finally, at the end, we took a look at a very simple case study where results from indentation plastometry were used to identify differences that had occurred because of the heat treating process that was undergone. And with that, I would like to finish and possibly hand back over to Jamie and or Sarah to drive the question session.
Yes, thank you very much, James. That was actually really interesting. I certainly learned a lot just recapping some of my uni work that you did right at the start, going back to stress strain curves. So that was really useful. And yeah, I would invite anyone to start to put some questions in the chat function on Teams. So we've got another 10 or 12 minutes or so just to answer some of the questions. If you'd prefer, you can unmute your microphone and ask your question that way instead. So just give you a couple of minutes just to think of some questions. Okay, that was quick. So we had one come through already.
Excellent.
So we've got one. So the indentation plastometry looks fascinating. How expensive is it relative to a tensile test machine?
Okay, straight to
commercial question, straight off the bat.
Commercial question. Let me mention a couple of things. We've deliberately tried to pitch the cost at a space which is in between that of hardness testing and tensile testing. One can go out now today and buy a hardness test machine for 5k, maybe even less. We bought some ourselves, or we did when we was at the university, for £5,000 each from China. They work perfectly fine. Or you can go out and spend 70 or 80,000 pounds on a hardness test machine, get all the bells and whistles. But at the end of the day, both machines are just measuring hardness numbers. What I've tried to convey today is that the hardness number is of very limited engineering utility, actually. Although sometimes people say, well, what else can I do? And that's perfectly understandable. We would now say indentation plastometry, but that's a different story. You can then go out and try and buy yourself a tensile test machine. Okay, and you know, a starting fairly simple model will set you back £40,000. You can go all the way up to £250,000 if you want. Again, if you want all the bells and whistles and automated swap out and things like that. You then need to buy all the peripherals like your strain gauges or your DICs or whatever it is you want to do, or your furnaces, and that rapidly ramps up the cost. And then you also need someone who's reasonably competent and comfortable operating the machine, so you've got some operational costs to consider. Our commercial price, well, I won't say it out loud today, is designed specifically to be in the middle of those to make sure it's competitive with both, actually. But what I would say is that while it's competitive commercially, it also offers the best of both worlds technically. Okay, so it's giving you hardness numbers if you want, it's giving you stress strain curves if you want, strength parameters, and it's got additional features which give you more insights that we haven't talked about today that I'd be happy to talk with people about for a separate private call.
Absolutely, and we can share your details out with the audience. Obviously, this presentation has been recorded as well and will be shared at a later date.
Definitely glad I didn't announce the price then.
Yeah, yes. Yes, if anyone has got those kind of questions, we can pass your information on and get that meeting set up.
Thank you.
So we've had another question come in that says, if we can't use ductility for meaningful engineering, what about percentage elongation?
Good question. And the answer is yes. If you're talking about uniform elongation, go ahead. That is meaningful. You can use that. Just don't use the ductility value. But the uniform elongation part of the stress strain curve is relevant. And if you take different dimensions on that, that's fine. You'll get the same thing. Okay, it's a uniform plastic straining. Okay, so go ahead to heart's content. And importantly, if you use indentation plastometry, we can tell you what the uniform elongation strain is.
Okay, and then we've had a follow-up to that question as well that says, can you test at temperature using the machine?
Good question. The answer is today, no. Q1 next year, Yes. So if people are interested in high temperature testing, come and talk to us. That project of ours is underway at the moment. We're expecting to release it to the market, as I said, early next year.
Okay.
And if people are interested, we're looking to be able to achieve temperatures of up to 800 degrees.
Fascinating. So looks like we've got 3 more coming in. So another one asking about whether the technology is patented.
Good question. Some aspects are. If you look at the hardness of the machine itself, it is a hardness test machine essentially, operating the same sort of principles. You've got loading frames, profilometers measuring shapes. You can't patent that. I mean, there's loads of examples of hardness test machines out there, and tensile test machines, and AFMs, and profilometers. Okay, even as the aggregate sum of all those things, it's not really going to be patentable. But we do have 1 or 2 patents associated with the technology, which protects us in a couple of different ways. And then, of course, our software in the background, software too, is quite difficult to patent, but there's an awful lot of know-how and experience and prior understanding which has gone into that, which is would be very difficult for challengers, really.
Okay. Next one we've got coming in is what is the minimum recommended material sample size for plastometry testing?
Great question. It depends on the size of the indenter that you're using. So when we supply our machines, we send 2 indenters. One's got a 2mm diameter and one's got a 1mm diameter. Okay, so as I've said before, that's quite large relative to nano indentation testing or even Vickers indentation testing. And that dictates what the minimum sample sizes are. So if you're using the 2mm diameter ball bearing, then we say the minimum sample dimensions laterally are 5mm by 5mm. The reason being is we don't want people to be indenting too close to a free edge. And if you indent too close to a free edge, that can distort the shape of the profile, the shape of the indent, and therefore it sort of undermines the modelling assumptions that are taking place in the background. And the thing that's then relevant is it also governs how thick the specimen can be. So for the 2mm diameter ball bearing, we say the specimen should be at least 2mm thick. Okay, and that is because we indent typically to depths of about 200 microns. Okay, so again, that's much deeper than a nano indentation test. But if you indent very, very thin samples, then the modelling assumptions, which assume semi-infinite sample dimensions, also break down. If you go to our 1mm diameter ball bearing, then those minimum sample dimensions shrink as well. Okay, and for those that are interested in testing things like very thin sheet, so let's say sub 1mm thick sheet, we're about to launch as well, sometime hopefully later this year, a dedicated module for thin sheet testing as well. So anybody interested in that, then please reach out.
Okay, and related to that question, I've got a question for myself, is for smaller components that would fit in the testing volume, can it be used as a quality assurance method at the end of a production line, for example, to ensure that you have got the parameters you expect after, say, welding or such as like additive manufacturing, you've got the layer heights and things like that as well?
Yeah. So you absolutely could put this at the end of a production line or somewhere in the middle of a production line and do some quality assurance testing in the same way you might do with a normal hardness test. Okay. Again, we would say actually that you get more meaningful information from indentation plastometry because you get stress strain curves. And as we highlighted, suppose you're on a production line, it's going through a furnace or something, there's a heat treatment taking place. What happens if that temperature is out for some reason? You get a slightly different stress strain behavior in the material because it's been annealed slightly differently maybe. But we've seen examples, and we know examples of where you got 2 different stress strain curves, but we'll give you the same hardness number, and maybe you don't therefore pick up that something's happened in that process. Okay, whereas with indentation plastometry, you would see it. Okay, so you can absolutely do that. There's an issue therefore around standardization. If you want to use a technology that's been standardized or accredited, or is conforming to some British standard or some international standard, then you need to think a little bit differently. And just to clarify, our technology is in compliance with both an ASTM and an ISO standard on instrumented indentation testing. Okay, and then the latter part of your question, Jamie, because I didn't write it down, I've sort of lost. Could you just remind me, please? These are additive manufacturing and layered structures. Yeah.
Yes, so it was essentially as obviously when you're producing additive manufactured parts, you have the layer heights, and I'm assuming that depending on the orientation in which you test it, changes your parameters, whether you're going like in between the layers or on top of the layers.
Yeah, okay, so what you're describing here, first off, the additively manufactured space is really important to us because historically it's been very difficult for people to test their AM components, or extremely expensive to continue printing tensiles in different directions and whatnot. And what you've highlighted there, Jamie, something that's important with AM specimens, you can get all sorts of things like different layers. Okay, maybe if you're doing something like wire arc additive manufacturing, for example, or you can have graded structures if you're changing the processing parameters, or you can get graded structures because the heat flow is different near to the base than it is at the top. You can get things like anisotropy, texture, porosity, all of those things which make characterizing additive manufactured materials quite difficult, actually. But one of the things you can do, or some of the things you can do with our machine actually, is that you can probe individual layers, provided you're satisfying these constraints that I've mentioned around interrogating representative volumes of your material. So if you've got quite a thick layer, let's say it's a wire arc additively manufactured structure, and you're in a particular layer and you're capturing all the microstructural features relative to that layer, then you'll pull out the properties for that. And this is related, if you like, to inhomogeneity, but you can spatially map properties with a technique like ours. Okay, so you could go from layer to layer to layer, or from space to space to space, and look at the variations. It's actually quite a powerful technique for doing this. And again, instead of getting hardness numbers, you can get stress strain behavior. Okay, and that is much more meaningful, far more useful.
Yeah, it sounds incredibly useful, actually.
Yeah.
So it looks like so we're actually running close on our limit on time, but we've got a few more questions that are coming in.
Sure.
So if everyone's okay, I'll just keep firing a couple of these questions
Yeah,
at you.
I'm
We get
good.
to them
I'm
pretty
good.
quick.
Yeah.
So had one that comes in. Does your method cope with surface and case hardening, and can it measure core properties in this case?
Another really good question, and the answer is this all depends on scale. So let's suppose we've got a case hardened layer that is hypothetically 10 microns thick, but we are indenting to 250 microns. Then the contribution of that 10 micron thick layer to the observed behavior is going to be quite small, almost negligible actually. And what we'll really be interrogating is all of the material beneath that case hardened layer. So the stress strain curve that we pull out or infer is really the underlying or the bulk mechanical properties beneath the surface layer. Okay. Let's suppose that the case hardened layer hypothetically is 200 microns thick and we indent to 100 microns. Then really what we're probing there is the case hardened layer. And therefore what we infer is the case hardened stress strain curve. Okay, so it's all about scale, and it's all about people understanding what it is they're testing, what the machine is doing, and using the system and approaching their testing in an intelligent way. It's what are you trying to achieve with the test? And the problems that you're identifying here, or the questions you're asking, are relevant not just to indentation plastometry, but to hardness testing. As well, anything that's sort of like local surface-based property measurement, you need to think about these things. So it's not unique to indentation plastometry. What we do have in our software package, though, is a facility which allows you to do something called multi-depth indentation testing, which means you can indent to a depth, let's say 50, come out, measure, get the stress strain curve, go back in the same location, down to 100 microns, measure, stress strain curve, and do this. You go 50, 100, 150, 200, 250 microns. And you can start to build up a profile of what the stress strain curve behavior looks like the deeper you go. And what we would expect is the deeper you go, eventually those stress strain curves will start to converge and fall upon a single stress strain curve as eventually you start to essentially interrogate mostly just the underlying layers, the underlying bulk mechanical material. That's what I mean. So lots to think about there. But again, happy to pick this up with people independently if helpful.
Absolutely. And some of the other questions might look like you might get some some follow-up. We've got a question here that says, can you provide some information on the science underpinning the generation of the stress strain charts through an indentation?
I can. And we tried to do this, albeit in a very simplified sense, by showing what the algorithm is doing, because that's where the science is. Okay, the machine is just a test machine. Okay, but what's really useful or helpful for us is the software. What's going on, and it is an inverse finite element analysis technique. So, and again, conceptually, that's very, very simple. Okay, we are just comparing a predicted profile shape with a measured one. And we're sort of saying to ourselves, well, what properties did the material have to have to obtain a profile shape like that when it was indented under those conditions? Okay, so how do we go? What's the process to get from this unknown material properties to known material properties through this profile shape. Okay, so it's an inverse finite element technique, and that's a standard methodology. It's very robust, and in fact we published a lot on this in the past. But if you want to know a little bit more about the underlying mathematical methodology, as far as I can say, so as not to release any intellectual property, we implement in our software package just a very bog standard FE approach with a continuum-based plasticity equation. It could be one of any number, Volche or Rambo-Gosgood or Ludwig-Coleman or others, whatever. And then we adopt just a very simple von Mises yield criterion to drive the plasticity. So it's all driven by deviatoric stresses. Nothing there about hydrostatic stresses, which is why, for example, we can't use our technique on highly porous materials, which compact, and therefore hydrostatic deformation becomes important. Okay, so again, to put it very clearly and succinctly, it is just an inverse FE technique with a von Mises yield criterion and a consistent continuum plasticity equation with a sprinkling of some clever optimization that I can't tell you about. Apologies.
And it leads quite nicely onto the next question, actually, was about how is the FEA model created? Is it done by the system or done by the user?
It's done by the system. So anybody coming to our software package needs no prior experience with FE modeling or optimization or mathematics or anything like that. It's all handled natively and in a way which allows you just very quickly and simply to be up the curve, pressing the go button and getting your answer. You can be trained up in 20 minutes to do this whole thing, and that's deliberate. You know, we don't want people to have to wrestle with this thing.
Yeah. And then we've got two more final questions. So we've got one that is, how do you intend to break into the world of standardized material testing when the standards stipulate the use of a UTM?
Great question. I hope someone's got the answer for me. It's a good question. So one of our entry barriers actually is standardization. Okay, there's no point me denying that. As I've said, we're already compliant with both an ISO standard and an ASTM standard for instrument and indentation testing, but often what we're competing with is people saying, well, I'm trying to do my test using a conventional tensile test machine because that's what the standard says. And that's fine. And it might be that in those instances, that's a place where we can't break into those markets. What you might find is that as and when our test technique does become formally standardized, and we're working with the ASTM and the National Physical Laboratory right now to do that, that people will start to migrate quite naturally because there's economic drivers to do so. Okay, so if you're spending hundreds of thousands of pounds a year machining test coupons and or employing people to do mechanical testing for you and or outsourcing that testing work, then if you come along to a standard which says, there's a test machine out there which can remove that economic burden from us, then you might find people starting to make the switch. So it's going to be driven by markets in the end. Okay, so the incentive for us as an organisation is to get our test techniques formally standardised as quickly as possible, and that opens up all sorts of markets in more conservative markets like aero, space, or defence, etc. Meanwhile, though, there's an awful large market being driven by things like R&D, where there simply aren't the same constraints around standardisation or certification. You've got people in laboratories who are doing blue skies research or other types of research where it's not so important that you conform into a particular testing standard. And that's where we're operating right now.
Okay. And final question that we've got in is, can this be related to material fatigue?
So that's a broad question. It's probably yours, Jamie. I know you're a fatigue guy.
Yes. If that question wasn't asked in the chat, it was one I was going to ask.
Good. It depends. Clearly what we don't do in a test like ours is any type of fatigue type test. There's no cyclic loading. It's a very simple, quick test. You can't use it, for instance, to generate an SM curve or something like that. Where you can use it, though, is that, if you're doing fatigue lifing calcs, for example, you're going to have to go out at some point and measure an SM curve if you're using an SM curve type approach to your fatigue modelling. There are others, of course, energy-based or whatever. But if you're using, I don't know, for example, FE-based live prediction or fatigue calculations, then you need to specify the mechanical material properties as well in there. And sometimes you need to do that as a function of temperature, maybe. And sometimes you need to do it as a function of material degradation. So if your material property degrading with fatigue, then if you've got specimens that you've been through a lab through that SN curve and you've got them at different stages, go in, indent them, get the properties. So my answer is yes, you could. provided you understand what it is you're trying to achieve and what you need to do to get there. If you need stress strain curves to support your fatigue calcs, we can help.
Great. So we've not had any more questions come in, and we've run over a little bit as well now. So if there isn't any other questions that come in, I think we'll draw it to a close. So yes, thanks, James, once again.
My pleasure.
We've had a few comments coming in saying great presentation, and they really appreciate your candid answers. And thank you everyone for attending the seminar. So again, I'd remind you that this was hosted by the Engineering Integrity Society, specifically the Young Engineers Forum branch. We hold regular free seminars and webinars aimed at supporting those at starting their engineering careers, which is what the Young Engineers is all about. If any of your colleagues or if you've been invited by a colleague to on this event, then you can email Sarah where the invite would have come from. So it's info@e-i-s.org.uk, and she can add you onto the mailing list. And we also run regular seminars, conferences and exhibitions through throughout the year that can be, you can get informed by that information on the mailing list as well. So just find what we've got coming up. So we've got another webinar on the 29th of June on the basics of transducers for materials testing and how to use them. So if that's of interest to you, you can see the email at the bottom there and the contact details to contact Sarah and get registered for that. And then the exhibition is a fantastic opportunity to get together and see all of the tools like this, plastometry and things like that from all the vendors that are members of EIS. We'll get together, and we also have a mini seminar kind of forum on the side where we discuss various topics. And that's hosted at the Silverstone Race Circuit in the wing, and this year it's at the 14th of September. And hopefully, COVID permitting, everything's going to be absolutely fantastic, and we'll all see you there. So that's about it. So thanks once again, James, for presenting, and thank you everyone for attending.
No problem. Thanks everybody.